Okay, this is section 2.6, combining functions. Let's go over a couple examples let's see. So what they'll do is they'll give you two functions. In this case, they give us f and g, and they'll ask us to either add these two functions together, subtract them, multiply, or divide them. So as we take a look at the addition, all we're asked to do here, I'm going to color code this, is to add the two rules together. So if I have f plus g, that means I'm taking the rule for f, which is x squared plus 1. I'm going to take the rule for g and add it to that rule. So plus 2x minus 5. Typically, you'll get a case where you can combine like terms. In this case, we do. So we get x squared plus 2x minus 4. They could ask us to subtract these two functions. Well, let's see. If f says the x squared plus 1, and then we will subtract our function g, which is the 2x minus 5. Be careful with the signs here. We're going to get x squared plus 1 minus 2x plus the 5. And my resulting function is x squared minus 2x plus 6. They could ask us to multiply these functions together. So let's see what happens when we have that. That's x squared plus 1, and we're going to multiply that by 2x minus 5. All right, let's FOIL this out. 2x to the third minus 5x squared plus 2x minus 5. No like terms to combine, so that is our answer. And finally, they could ask us to divide these rules together. So let's see, they want f divided by g, so that's going to be x squared plus 1. And we will divide all of that by the rule for g, 2x minus 5. So with nothing to factor, nothing to cross out, my final answer is x squared plus 1 and 2x minus 5. They also ask us for the domain and range, just the domain, all right? Since these are polynomials, the domain is going to be all real numbers for the given functions and for the combining of the two, except for the last one. All right, there's a red flag down here. Let's see, there's a red flag because when we have division, we can't divide by 0. So what we need to do is take the 2x minus 5 and set it equal to 0. That will give me x equals 5 halves. I have to avoid this particular value of x because that will make a division by 0, and we need to avoid that. So in this case, I would say the domain is going to be all real numbers except for 5 halves. So that's negative infinity to 2.5, union 2.5 to infinity. All right, here's the definition of the composition of two functions. Given two functions, we can compose them together, and here's our notation, and here's another way to write it. We're going to have to talk about the domain of f composed with g. It's the set of all x's in the domain of g, such that g of x is in the domain of f. In other words, this is what we're going to say. The composition is defined whenever both g of x and f of g of x are defined. So for the domain of f composed with g, we're going to set that equal to, or we're going to do this. We're going to find the domain of g, and we're going to intersect that with the domain of f composed with g. All right, so here's an easy example. Notice for each of these functions, the domain is equal to all real numbers for both of these. And so to find the domain of the composition, let's first find the function. F composed with g is putting the g function into the square, so that's x minus 3 squared. And then g composed with f is putting the f function to g, so that's going to be x squared minus 3. Notice the domain of these two functions are all real numbers, so we would say the domain of f plus g is the same as all real numbers, as is the domain over here. When they want us to compute numerical values, we'll do it this way. We'll say f composed with g of 5 is the same as f of 5. Well, when 5 goes, excuse me, it's the same as f of g of 5. When 5 goes into g, g says we're going to subtract 3 from that value, so it's going to be 5 minus 3, which is f of 2. And then 2 is going to go into f, which says we square it to get 4. The next numerical value is g composed of f of 7. Let's see, that's going to be g of f of 7. So f goes into g first. F says we're going to take that number and square it. So that's going to be g of 49. And then 49 goes into g, and g says let's take 3 away from that, which is 46. All right, here's an example where we have to find a composition and have to find its domain. Let's start by finding domains of the given functions. F is going to be, the domain is going to be all values. Let's see, I know that x minus 4 must be greater than or equal to 0. So x must be greater than or equal to 4. So the domain goes from 4 to infinity. And then this domain is going to be all real numbers. When I want g composed with f, it's going to look like this. I'm going to write the g function, which I'm going to square something, right? That's what g says to do, and inside that I'll put the square root of x minus 4. So let's say that's going to be x minus 4. So when I find the domain of g composed with f, that's going to be the same as the domain of f intersected with the domain of g composed with f. Let's see, we already did f. F is going to be all numbers 4 to infinity, and let's intersect that with the domain of the given function, which is all real numbers. So notice the domain is going to be all numbers 4 to infinity. Even though our composition has a domain for all real numbers, we have to keep in mind that we're plugging numbers into f first. Okay, here's another example. Let's first find the domain of the given function, f. This domain is going to be all real numbers except for 0, because we cannot divide by 0. The domain of the second function is going to be all real numbers except for negative 2. When we look at the composition of these two, when we look at f composed with g, let's write the f first. That's 1 divided by, and then instead of the x, it's going to be 1 over x plus 2. Multiplying by the reciprocal gives me x plus 2. So once again, an example where we see that the domain of the composition is equal to the domain of the g. We always take that function there, the input function, which we said was all real numbers but negative 2. And let's see, that equals negative infinity to negative 2 union with negative 2 to 8 to infinity. And let's intersect that with the domain of the function we just found, which is all real numbers. So it turns out the domain of the composition is all real numbers but negative 2, even though our composition looks like it has all real numbers. Another example like that, let's see. With this particular f function, we have x must be greater than or equal to 0, so that's going to be from 0 to infinity, the domain of that. And let's do the domain of g. The domain of g is going to be, I've got to write 3 minus x must be greater than or equal to 0. Simplifying that, I get x is less than or equal to 3. So that's going to be negative infinity to 3. All right, so another case we have to worry about are discrete functions, mainly when you just have ordered pairs that represent functions. Doesn't change here. When I want f plus g, I'm going to have to supply an answer that looks like my original functions. So here, the input is going to be 2. It's going to be all the inputs here. I have 2. I can't put 4 into both functions, but I'll have 7. I can put a 7 in both functions, but not 4 and 5, because the domain of f plus g has to be in the domain of f and g. So The output here for the 2 is going to be 3 plus 5. That's the y values for both functions. And when 7 goes in, I'll get 11 plus 2. So this particular addition of two functions looks like this. 2 is going to map to 8, and then we would say that 7 maps to 13. We could also subtract these outputs. So f minus g will have the same domain. We're going to find ordered pairs for 2, and we're going to have to find the ordered pair that has the 7. But in this case, we're going to subtract the outputs. So it'll be 3 minus 5, and then we'll have 11 minus 2. So this function looks like this. We will have 2 comma negative 2, and then 7 comma 9. When we compose these functions, let's start with the domain of the first function, which is g, and so we can put those numbers in there. So g is going to be, the domain is going to be 2, and then we will have 4, and then we can put in 7 into g. And let's see what comes out of those after those outputs go into f. So this is going to be f of, let's see, 2f of 5, and this is going to be f of 3, and when 7 goes into g, the output's 2, so this is f of 2. So when we put this together, we'll get the function 2 will be mapped, f of 5 is 4. 4 goes with f of 3, which is nothing. So we're going to put the null set there. And then 7 is going to be mapped with, let's see, 7 goes to 11. So really what we could do is we could eliminate this ordered pair since 4 is not in the domain of the composition. Let's do the other one. Let's show g composed with f. So we will do this. We will write the ordered pairs for the input of f. You can put 2 into f. All right, when 2 goes into f, we can put 5 into f, and we can put 7 into f. All right, so let's see. When 2 goes into f, the output is 3, so that's going to be g of 3. When 5 goes into f, the output is 4, so that's g of 4. And then when 7 goes into f, the output is 11, so that's g of 11. So just plugging these into the g function, when 3 goes into g, there is no output, so that's the null set. So 5 will be mapped with, let's see, when 4 goes into g, we get 3. And then 7 will be mapped with g of 11, which there is nothing. So we'll have 7 null set again. So we would eliminate these two from our set and say that our function is nothing more than 5 comma 3.